Hi everybody, and welcome to exercise 4 on page 63 of the workbook. And in this problem, they're asking us to set up an integral that gives the volume between a plane and a ball. Okay, now before we dive into this, I'd like to just try to draw a rough picture of this so we can picture the volume that they're asking us for. So z equals x squared plus y squared was the ball-shaped surface that we called a paraboloid. We saw that very early on in the course. And the plane z equals 4 is just a horizontal plane, so to speak, at z equals 4. So imagine a flat plane sort of chopping the top of our surface off, and that's what the entire volume is going to look like. Now let me superimpose an x, y, and a z axis here. Okay, so there are our coordinate axes. And we'd like to find the volume of that ball-shaped thing that we just drew to the right. Okay, well, how can we do that? Well, one way to think of this is to break volume down into its component parts. Okay, we can get a volume by taking a height and multiplying it by an area. Okay, now what do I mean when I say height? Well, to picture that, imagine just picking a point on the bottom of this ball and going straight up until you hit the top of the region. Okay, so think of that as a really skinny little rectangular prism that we just drew. Okay, and ask yourself, how would you measure the height of that? Well, what you could do is just ask, what is z equal to at the top and the bottom? Okay, we know that the top of the region is that flat plane z equals 4, and the bottom is given by the equation of the ball, which was x squared plus y squared. So the height then we could get by just taking the difference between those two things. Subtract the z at the top from the z at the bottom. Okay, that means that this integral is going to turn into 4 minus x squared plus y squared times dA. And just to do a quick unit check, if we assume that all of our distances are measured in meters, height is going to be measured in meters, and area is going to be measured in meters squared. Multiply those, you get meters cubed. Those are the correct units of volume. Okay, but now we come to the question of, what is it that we're really integrating over? What is this r that we're talking about? Okay, well, to figure that out, you can think about this shining the light technique that we've been talking about. The region R will appear if you imagine shining a light straight down the z-axis and asking yourself, what would the shadow look like down in the xy plane? And you can probably picture this and come to the same conclusion that our shadow down here should be a circle. Okay, and I apologize for my drawing skills. That's my best attempt. Okay, that circle is actually exactly the same size is this circle up here because that's where our region is the widest. Okay, so to complete this problem, we need to actually find limits of integration here. Okay, if we break this up into an iterated integral, and let's just choose a direction, maybe go dy dx. How do we know what the range of x and y values are? Well, to answer that question, we need more information about how big this circle is, okay, on the boundary of R. And to figure that out, it really comes down to looking at this curve at the top and determining how wide that circle is, what its radius is. And the thing to notice is that that circle that we highlighted, the green circle, is the intersection of our two surfaces, z equals 4 and x squared plus y squared. It's a curve of intersection. Okay, and we can calculate that down below. Okay, between, z equals 4 and z equals x squared plus y squared. So think back to algebra for a second here. If you want to figure out where two curves or surfaces cross, what do you do algebraically? Generally, you set them equal to each other. So if we want to know where those two surfaces cross, we're just going to take x squared plus y squared, set it equal to 4, and ask, what does that equation represent? Well, that's a circle in 2 dimensions of radius 2, x squared plus y squared equals 2 squared. Okay, let's draw a separate picture of that circle, just in 2 dimensions. Sometimes we call this a projection picture. Okay, we know its equation, and so we know that the radius is 2 here. And that's the region that we need to integrate over in order to figure out what the limits of integration of this integral up here are. Okay, now we chose to integrate in the y direction first, so let's draw a typical rectangle in the y direction. And what we need to know then is what is y equal to at the top and at the bottom. Okay, notice that we're going between 2 curves because this is our inner integral. And so we can figure that out by just taking this equation for the circle and solving it for y. Okay, so y squared equals 4 minus x squared. If you solve that for y, you get plus or minus the square root of 4 minus x squared. And turns out that the top curve is the positive square root and the bottom curve is the negative square root. Those are the 2 curves that we're going in between, and so those give us our limits of integration in the y direction. Okay. Let me try to be a little bit more careful and write this neatly. Okay, so we've got our limits in the y direction, and now, again, once we're done with that inner integral, the x limits are always just going to be ordinary numbers, and we're going to shine the light to figure out what the shadow is, to figure out our x limits. This time, notice that part of our region is below the x-axis, so we're going to be shining a light from the top and the bottom in this case to get our shadow. And so if you do that, you shine the light from the top and the bottom, your shadow is going to be sitting here. Okay, and then ask yourself, what's the range of x values? Well, we're going from -2 to 2 because 2 is the radius of our circle. Okay, and so those are our x limits. And if we go back up to the problem itself, it said set up but do not evaluate, and so we're actually done at this point. Okay, this iterated integral that we just set up is our answer to this question. Okay, we're not going to evaluate it because the limits of integration are a little bit ugly. That would be a little bit tedious to actually do the details.